So good morning, good afternoon, good evening, depends where you are. So we are here today for a very interesting talk, industrial talk related to Lumentum, a new company in the state of Campinas, talking about opportunities on high-speed IC design. So we have three speakers from Lumentum today: Jacklyn Reis, Daniel De Lazari, and Nelson Andrade. So, but today we are here to attend the talk about Lumentum, opportunities on high-speed IC design. So the talk will be given by Jacklyn Reis, Daniel De Lazari, and Nelson Andrade. So Jacklyn has over 15 years of experience in optical communications, focusing on high-speed optical transmission, network, and digital signal processing. As director of microelectronics at Lumentum Holdings, he leads more than 60 engineers developing digital signal processing ASICs for optical transceivers in deep submicron nodes. Daniel De Lazari uh, has over 29 years of experience developing ASICs, FPGAs, and hardware systems, engaged in several system on a chip design phase, such as system architecture, RTL coding, performance power analysis, IP integration, timing constraint synthesis, module and top level verification, static time analysis, chip layout, gate level simulation, and FPGA prototyping and software interface. And Nelson Andrade is an electrical engineer with strong qualification in IC design, with focus on analog RF design. He's been working for over 7 years in this area and has experience with IC design from transistor level to full chip tape out, including high speed circuits and FinFET technologies. Currently, he's working with high speed converters for optical communications. So, thank you very much, Jacqueline, Daniel, and Nelson, to uh, give this talk today. And I give the floor to Jacqueline to start the presentation. Thank you very much.
Thank you, Professor Reis. Thank you, everyone that is attending. So, good morning, good afternoon, good evening. So, it is a pleasure to be here, and it's very exciting to see all the activities happening inside CAS and Rio Grande do Sul chapter. So, that's amazing to see all the effort to bring the community together, and it's amazing to see the technology, the microelectronic technology. And semiconductor uh, growing uh, growing a lot in the region. So yeah, so it's we'll try to cover and take this opportunity to share some of the activities and potentially opportunities that we have here inside Momentum, inside the high speed IC group. So I will share a little bit of some of the activities about the company and our history. And Daniel De Lazari and Nelson Andrade, they will help me, and we'll try to cover as much as we can and also to have some time in the end to reply to some of the comments and questions that may arise. So next slide, Nelson, please. So yeah, so we'll try to cover what we are doing inside Lumentum, and you can go forward. So yeah, so just before we're getting into the details of what we are doing, so before joining Lumentum, we were Idea Group located in Campinas. So we were split in three different companies. Idea, focusing on research and development on three different areas: microelectronics, photonics, and product engineering. We also have PyTech, system and module manufacturing company, focus on scientific instrumentation, coherent optical transceivers, and IoT devices. And BL Photonics, focusing on silicon photonics transceivers, tunable lasers, and integrated photonic devices. So these were the structure of our group up to August this year. Uh, After a while, we have been working very closely with other companies. And since August this year, we joined Lumentum Holdings. Uh, and today we are part of Lumentum. And all these activities happening in Campinas and in our different sites that we had, covering many aspects of our development. We have joined Lumentum to leverage all the, let's say, all the strategy, the infrastructure, and the roadmap for the technology that we are doing here in Campinas. So you can go for the next slide. Uh, Nelson. So just for those of you that doesn't know about Lumentum, so we are a world-leading optical component and module supplier. So today we are a company that we have around $2 billion of revenue. So that was our numbers from the fiscal year 2022. So we have about 8,000 employees globally, more than 2,800 patents and applications. And we have a very strong position, especially on telecom components and modules, high-speed data center laser chips, and 3D sensing diode lasers. So all this information that we are seeing now, those are public information that you can take a look in our website for more details. So our revenue is split mainly on 60% of telecom and datacom, 9% lasers, and industrial and consumers 24%. So this is more or less how our business are split among the different units. So for the next slide, you can see all our infrastructure. So we have a global presence close to our customers. We have R&D and operations across the globe. You can see here on the Americas, on EMEA and APAC. And you can see there in Brazil. So we have our site in Campinas that was actually that was a new building that we just opened last week. So this is where we had all our R&D activities on DSP, on X-ray, and on photonics development. So in the next slide, you can have an idea on uh, you can go ahead to the next one. Yeah, so you can see all our wafer fab infrastructure. So we have wafer fab in the Americas, especially in US, covering different processes like gallium arsenide, indium phosphide, uh, and we also have PLCs, silicon fabs, and to cover different components and product lines. In Caswell, UK, in Europe, we also have indium phosphide, and in Japan, we have other wafer fabs to cover different product lines. For instance, to cover data center lasers and PAN4 EMLs, GaN chips, and so on. So in the next slide, you can have an idea on our main business units. So we have five business units: telecom transport, telecom transmission, where we are here in Campinas, datacom and commercial lasers, and 3D sensing. And in this talk today, we'll focus on the analog and digital coherent module components development that we are doing here in Campinas. And in the next slide, Nelson. So inside the next generation 400 giga plus networks, one of the key components, of course, that are the main product that is the optical transceiver module, where we have the lasers, the optoelectronic devices to do optoelectronic conversion. We have the coherent DSP, so it's an SoC that has millions of transistors integrated using state-of-the-art transistor technology. And this will be the main focus of our talk today. So as I mentioned to you, after the acquisition, we have been focused quite a lot on that aspect of the technology that we are developed in Lumentum. And we will cover mainly the main expertise and some of the history, the prior designs that we did before the acquisition. So you can go to the next slide. So one of the key components of our strategy is to be vertically integrated, right? So as Lementum, it's very important for us to deliver the best quality to our customers, to have all the key components being developed inside our organization in order to manage customer satisfaction, right? So we know that it's a very important aspect to not only deliver a good products, but actually those product has to, let's say, be compliant on the needs of the customers and in the end customer, right? So that's why it's very important for us to have a vertically integrated technology platform. And you can go to the next slide. So that was the main, that was a summary introduction for all of you that is joining us today. And now we are going to focus on the next aspect of the development, and hopefully in the end you can have an idea on what we are doing, and maybe raise some questions and comments about the opportunities that we are having here inside Lumentum. So you can go to the next slide. And I will hand it to Daniel De Lazari. Lazari. Professor Reis, I think you have to hand the presentation now to Daniel De Lazari, that he will cover the expertise and background.
Oh, okay. Hi. I'm sorry about that. Yeah, so now we're going to talk a little bit some of the things that we did on the past, and our capabilities, our flow, and so on. So from 2016 to 18, we did a chip that the speed was around 100 gigabits per second, and that was done like in a 28 nanometer. And the maturity level, we did like design, tape out, silicon validation that end up going to a module for testing in the module itself, in an optical module. Then we moved to 400 gig ZR. That's like much higher speed and a new protocol. And at that time, we switched to 7 nanometer and below. And this one, we did the design, tape out, and silicon validation. And we also designed a much more like multi-mode chip. That's this one on the right. And so these are basically the standards that we cover, starting with 100 gig and then 400 gig ZR, 400 gig ZR plus, and the next on the roadmap is the 800 gig. And the team that we have covers like almost the entire flow. So we start with spec and modeling, like looking on the standard, what's required there. And in terms of all the fiber impairments, we have a lot of things to compensate depending on the speed, depending on the optical components, on the fiber quality, like chromatic dispersion, and all that we are able to model that. So we don't receive that spec from somebody else. We have like high level models before we get to RTL that point us that, oh, this algorithm will be able to cover what we need to do. Then we enter on the flow, like traditional ASIC flow, where we have digital and analog design. And then we get up to tape outs. Those are the figures of some of these tape outs that I described on the top. Below are the actual images. And then after the tape out, we also get involved into silicon validation, with firmware and software development and checking if everything that was modeled, if everything was done correctly. And some of the, in some case, we're able to prototype some of these in FPGA. That occurs like in parallel. But that one, like usually our ASICs are very big, that even if we take the largest FPGA in the market, it's usually like we cannot fit even 1/4 of our ASIC, but we try for the specific modules, for things that we need to run for a longer time, like error correction that you need like 10 to the minus 15. So we do FPGA testing in some case, and the silicon validation, and below is the example of some boards and some of the chips. Yeah, you can go to next one. Yeah, this one provides a little more detail what's covered in each phase. So I mentioned briefly the spec and modeling. So we go from system requirements, models for the DSP and the FEC required. So a lot of stuff is required by the standard to be interoperable. So those are like must requirement, but you have how to achieve that, correct? And the power is always has been a very challenging point for us. Because these modules, optical modules, they are very small. They go in the big switches with so many of these modules that the power dissipation is one of the major challenge. I mean, despite, of course, to be able to operate at those frequencies. But the module, like if the power doesn't go below a certain level, you cannot even put into a module. So this entire flow, the power is always there, but since the beginning, since the spec and modeling, we're already like worried about that, concerned about that, and trying to measure that in every single level. We're measuring power, and as we go more to the right, we get more precise in the power measurement and the power estimation, but it's too late to change, correct? So that's why we do that in every phase. Then the logic design that goes from RTL, physical synthesis, and of course power estimation. In parallel, it's running the verification with both RTL and gate level. Then we have physical design. Even for this low geometry, the physical design is also in our group is a challenge every time you go down a node, because you have multi-pattern, you have colors, you have many more DRC rules. The DRC deck just keep increasing. And that one, we always keep trying to develop new features for our physical design to be lower power. So we try to correlate all the time the logic synthesis power, physical synthesis, and place and route as well with the silicon. So that's an important point as well. Then once we create the database, of course, we need to verify physically, like a static time analysis, DRC, LVS, airdrop, and electromigration. In parallel with these disciplines, we have like a chip top where we need to worry about how to combine all these different IPs, digital IPs, analog IPs from our groups, as well third-party IPs that we also integrate. And our involvement doesn't stop, as I mentioned on the prior slide, doesn't stop with tape out, because we have silicon validation and the firmware and software development to put this into a module. Like these DSPs, besides being a DSP, they also have a processor inside, and what the customer sees is very much dependent on how well the firmware is developing. And the analog IP design is not detailed here, it's just like an arrow in the bottom, and Nelson will talk more about that. This group traditionally here in Brazil was smaller, and now we are increasing this capability, but that one runs in parallel with the other flow above. And that one also goes all the way to post tape out activity with silicon validation and so on. And DFT also runs in parallel with SCAN, MBeast, ATPG, and so on. I think I kind of, so, I mean, I think the main message on this slide is that in order to do that, to achieve the vertical integration that Jacklyn was talking about, I mean, we're talking with customers that a while back was external customers, now they are internal to the company, the guys that do the module, and we go from understanding the protocols. I mentioned a little bit the fiber, but we also have protocols on the Ethernet side, different 100 gig Ethernet, 400 gig Ethernet, and so on, that we need to cover. And we go from that phase to logical, physical, tape out and testing. I think you can go to the next one. Yeah, so this is an examples of some chips we did on the past. So this is the 100 gig 28 nanometer. That's like the layout. I mean, because it's an old technology, the chip was much bigger, like 80 square millimeters, and that's, you have like approximate cell count there. And these are some, the ASIC is complex, so we have several internal loopbacks that we can test before we get the analog to works. Then we can do internal and external communication. And the standards, they also provide some tests that you must support, and we do some other tests. And then we have to draw these curves with OSNR, bit error rate, and per chip, and so on. So there's a lot of tests to be done as well. This one is just to show more or less some of the designs we did on the past. So you can go to the next one. This is a 400 gig ZR at 7 nanometer. At the time it was Samsung, and we did some test chips because at this time the technology was in 2017, was very new to us. So we test some independent blocks like chromatic dispersion, like FEC, or the PAM4 on the host. So we did 2 test chips, and this work was concluded on the boundary of end of 19, beginning of 2020. And that one was the basis for the next chip. Can you go to next one? That we code name is Titan. So this is the OEF number that we are complying to. And on the right, you can see the like a layout view. So on the line side, we cover 60 gigabaud, and with this 16 QAM. On the whole side, those are the specs that we cover. And below you also have the size of the chip and the number of transistors. And this chip is really big. Even taking the most advanced servers, NEDA, we cannot run like top level altogether. You have to do like a hierarchical implementation where you implement certain blocks and then you kind of combine them together. And this was one mode, that this mode of operation is the 400ZR that's described here. We tape out this in the middle of 2021, and then we start working on, you can go to next one, that the code name is Viga, is also less than 7 nanometer. This one, the biggest difference it's multi-protocol. So several of these blocks now, they have multiple operation, what's put a big challenge on verification. And some of the name of the standards is ZR Plus, Open Rodent, and 100 gig cable labs. So if you count all together, comparing speed, host, protocol, line protocol, it's more than 50 modes of operation. So it's a very complex chip. And this was more or less what we have been working until we got acquired. And now our new plan, of course, is built on top of this technology that we have in-house, but the plans are being defined, and as we speak, is not so far from what we show here, but it's the exact thing we don't have yet to show, and we cannot show. But that's more or less our group has been working all these technologies. And basically, to cover this standard, we need to be very strong in DSP, very strong on FEC, that's the error correction. And this ASIC in particular, to be able to cover all these standards on the whole side, on the Ethernet side, you have so many protocols with different framing formats. So you have to be flexible to support all that and to be able to test all that, and of course all the infrastructure required like PLLs and CPU memories, debug memories, and so on to support that. And I think that kind of covers what we have been doing. You can go to next. And now I think Nelson will talk about the analog design challenges that we have.
So thank you, Lazari. Thank you, Professor Reis. I'll start talking more about the technical challenges that we have, more specifically the analog design challenges. These applications that both Jacklyn and Lazari talked about, they are mainly driven by the digital design team, and we from the analog design, we try to catch up to them, and it's not a simple task to do. So I'll try to cover some of the challenges that we have to face to deliver these chips to the market. So basically, the first challenge that I wanted to talk about is about speed. As we've been talking, the circuits that we made, they are very, very fast. The sampling rate is incredibly high, and we have converters, both analog to digital and digital to analog converters, operating at above 60 gigasamples per second. So it's a very high sampling rate. And these circuits, they have to meet high performance standards. They have to meet SNRs, to meet bit error rates, all while operating at this frequency. And also, we need to worry about power. So for us, it's always a battle between power and performance, how to achieve the performance that we need for the standards without burning the chip with heat. Apart from the raw sampling frequency and the baud rate that we need to deal with, we have actual clock generation and distribution. We have actual clock signals going inside the chip above 5 gigahertz. So those are very high frequency signals to be dealt with. And we need to care about the signal matching in the circuits. So we have some converters working in parallel, and we need to guarantee the clock distribution between those circuits. And the clock is running at 5 gig, and we need to guarantee that this clock arrives at the perfect timing to all of the converters, all of the cells. And also, apart from timing, we have to consider jitter. So here we can see an example of a measurement of an internal signal that we expect to be a square wave, a pure square wave, but we have some distribution around the ideal transition slope, and we need to keep this at a minimum variation. We have some tolerance around that, but we need to make our circuits very low jitter. So for both of these concerns, that regards to speed of the analog operation, all the parasitics of the circuits matter a lot. So everyone that has worked with analog circuits knows that there is a difference between pre-layout and post-layout simulations, and usually it can be dealt with easily, but for such a high-speed circuits, we need to consider the parasitics all from the beginning. We need to estimate them and to set targets for our parasitics in our layouts. And also, after the layouts are done, we need to check and verify that all of the parasitics are under our tolerance. And for these, we have, besides the normal tools that we use for the analog design, we also have some extra tools that we use only to analyze parasitics after the layout is done. So during the whole process, from the schematic design all up to the final sign-off of the chip, we worry about those parasitics. And talking about them, we actually use PDKs with FinFET technologies. So to achieve these ultra high speed circuits, we need to use these advanced nodes PDKs. Also because we, as I said, we are driven by the digital design, and the FinFET transistor provides us with the faster switching times, and it guarantees that we have the fastest circuit that we can. From the analog point of view, we do have some advantages on using FinFETs because compared to the most recent planar technologies, the FinFET provides higher intrinsic gain, the transistor itself. So it's a plus side for the analog design. However, they present higher current densities and also higher density of the circuit itself. Since the transistors are very small, the routing becomes more relevant, and the parasitics of the routing becomes more relevant. So we use them to solve our problem of speed, but we need to deal with the extra parasitics that they bring together. Apart from the transistor itself, this advanced node PDKs, they present more layout complexity in general. The FinFET devices have quantized dimensions, so different from the traditional technologies that we use to design. The FinFET technologies, they presented fixed dimensions for the transition. So we don't have total freedom in designing the transistors themselves by changing the width and the length as we please. Instead, we need to follow the design rules and feed those transistors, fit those devices into a very strict grid. And as I mentioned, since the devices are so small, the routing becomes very dense, and we have an increased number of layers, of metal layers and contact layers to deal with. And this brings complexity to the layout design. And for these recent technologies, we also need to deal with multiple patterning strategies. So as you can see in the image on the right, sorry, the traditional process, the traditional processes have one mask per layer of metal, for example. So as you can see in the above layout example there, what you design on the EDA tool is going to turn into a photolithographic mask, and it will translate more or less directly to the layout. For the advanced nodes processes, since the dimensions of the routing are so diminished, we have this multiple patterning technique, which is basically that we have two different lithographic masks for each layer of metal. So for example, when I design routing in metal 1, I have two different layers for the metal 1 in the EDA tool, each one represented by a different color. And these different colors turn into different masks. And because of that, the foundry can actually achieve the fabrication of such small dimensions, because it basically reduces the distances and spacements of the masks by half, since I have to design 2 masks for the same layer of metal. And of course, all of these brings us to a huge amount of design rules. Since we have those different masks, there's a lot of different metal layers and also diffusion layers. And because of the narrow spacing of the devices and routing that we need to place, the design rules increase exponentially. We have a lot of them. We need to deal with a lot of design rules correction that are demanded by the foundry for our chip to work. Apart from the speed and the PDK, we also have some challenges regarding our application, because our circuits are so big and have to deal with a lot of protocols in ultra high speed. We need to verify this in simulation, and we have to guarantee the proper integration of different parts between analog and digital as well. And also we need to validate that after the tape out, after the circuit is fabricated. So the first step of verification that we take is the post layout performance simulations. That it is usual to do that in all of the technologies, but as I've said, the high speed and the advanced PDK make this step very critical. The validation of the parasitics extraction, the circuit after the parasitics extraction, it can be very different from the schematics view for us, and we need to make this validation as precise as we can. Also, for these types of technologies, the passive devices modeling can be an issue, and also the passive devices, when we put them to the layout, they can present different behaviors as from the schematic. So these post-layout performances are very critical. And since our circuits have a lot of devices in them, the netlist size of these post-layout extracted views also gets bigger, and the simulation time is also critical. And we need to think about strategies of simulation to actually achieve these simulations in a finite amount of time. So these are some challenges regarding the post layout validation. Also, we have to guarantee the system integration performance. So we design the analog circuits, and we need to integrate them in the digital system. And here, the power and signal integrity are critical for performance. We need to meet timing closure from the digital system. We need to perform some mixed signal simulations to guarantee that the timing is correct between digital and analog. And also, considering the top level of analog circuitry, we have used different tools to guarantee the power integrity, the power distribution. Since the circuits are so dense, we have been making use of such a tools to guarantee the power integrity. And to aid with the timing closure, we also have used some specific tools to guarantee signal integrity, to guarantee that our signals have the proper matching for the application. After that, we also perform chip validation. We get involved with that in our group. We, as designers, we also provide help for the validation team, and actually we get into test ourselves. After the chip is taped out, we go to the lab, we do some on-hand measurements of the performance of the circuits that we simulated extensively. And one thing that it's a very good aspect of our previous tape outs is that we actually get actual silicon data of these very advanced PDKs, and we can compare them to our simulations and make correlation between what we see on the silicon and what we see on our simulations, and build a correlation between them to incorporate these relations to the next designs too. And one aspect of the chip validation is also the equipment needed to do that. Since the circuits operate at such high frequencies, the oscilloscopes and signal generators need to be able to reach those frequencies, and we need some high-end equipment as well. But it's very nice to have the opportunity to test the chip that we worked on both design and the layout. To address these challenges in analog design, we came up to a different design flow for the analog circuits. This here that you see on screen is the very well-known analog design flow. We usually start with spec architecture, then we go to the schematic design, circuit simulation, and then we do all the layout parts of it: the custom layout, the layout verification, DRC, LVS, extraction, and to validate this in post-layout simulations. Since most of our challenges here, most of the issues that I've addressed here in the previous slides, they come from the match between layout and schematic. We need to make those as similar as possible. So in order to deal with it, we design things in a slightly different design flow. The initial part is basically the same. We make the specification, architecture, schematic, and simulation to validate the system, validate our concepts, and validate our topologies. And also, one thing that is different in this stage of design is that wherever we know more about the circuit and the layout, we also already include some parasitic estimation in the schematic in order to match better the schematic and the layout. But the thing here that is different from the traditional design flow is that we divide the layout in two phases. So instead of going to close the schematic and deliver it to the layout and making only small changes after the first layout is done, we actually make a quick schematic version of the circuit, simulated to guarantee that the system works, the topology works, and we deliver it as quick as we can to layout. So we perform a basic layout implementation, as we call. We need a basic implementation, so the floor plan, the routing, in this basic layout stage, the LVS must be clean for the simulation to work. And we actually don't care much about the circuit being DRC clean at this stage, as we would have been in the traditional design flow. We make the layout as close as we can to the final version that we picture, but without covering all the DRC errors that may arise, because the DRC list is so extensive that it demands a lot of work to bring the layout from its basic version to its final version. So we actually only need a LVS clean at this point with the approximated distance without any major modifications, and we make these as long as we can to guarantee the performance. So we make the basic circuit, implement the layout, check the performance, see what needs to be changed, and do this a lot of times until we are satisfied with the post-layout simulation of this first version of the circuit. And after we are satisfied with this performance, then we go to the final custom layout, the version that will be implemented. And we apply all the DRCs and make sure that all the DRCs will be clean, and implement some metal fill and all of the things that are needed for the sign-off. Actually, here in the final layout flow, we also have some particularities that there are some blocks that we need to implement some custom metal fill instead of the normal one, to guarantee matching, to guarantee the reduced parasitics. So there are some circuits, some portion of circuits that we can actually do the metal fill manually to guarantee performance. So this is basically it. Our worries about the layout being very, very close to the schematic as much as we can. So this is why we do this in a slightly different flow, and we do this through a high number of iterations in this process. So in order to overcome those challenges, we need to have motivated people to work on them, to overcome those challenges, and these challenges become then opportunities. So as we mentioned on the beginning, we are currently looking to expand our analog team here in Brazil. There is much work to do. There is many challenges to overcome, to deal with, and we are looking for some people to help us on this task, to expand our team, to join our team, and make those circuits with us. So we are looking for some people with experience in analog IC design flow, with strong technical knowledge of layout and simulation, and that can communicate and bring those projects to life, interfacing with different areas of the company. And one thing that is very, very motivating for me, at least, is that we can work with this high-end technology. It's a rare opportunity, and we can see, as I've said, we can see our designs turn into products. We make our designs, our layouts, all the flow, and we actually can see our designs taped out and go inside a optical module and test it on the lab and see it become a real product to the market and be compacted to the market as well. So I hope we have got your attention, and I hope we can have a few people interested in working with us to overcome those challenges. And so please contact us if you want to work with us, if you want to talk to us, know more about our flow, our design, our company. Please feel free to reach our HR department. Here is the email. It's under Idea IP domain. We are transitioning to the Lumentum, but for now, you can send an email to the HR here, and we'll be glad to share everything that we can and have interesting discussions with anyone interested. So thank you very much, And also, thanks again, Professor Reis, for having us here and giving us this opportunity to present our work to the community.
Well, thank you for giving this nice talk, giving an overview of what Lumentum is doing. So now for questions, if you have any questions, please do it very quickly using the chat channel of the YouTube. We have here a question by Philip Menezes from Unicamp Campinas. So in the analog design flow, the same designer is responsible for schematic layout and sign-off of a given block, or these are separate steps performed by different designers?
It is separated currently. We have the schematic ownership mainly on the team of the United States, and here in Brazil we started working mostly with the layout and circuit simulation and system validation. But in practice, we end up doing a lot of things. Usually one person becomes responsible for one block, one given a part of the circuit, and this person has a lot of interaction between the team here in Brazil, the team there in the United States, and the schematic designer and the layout designer are very close, up to the point that the layout designer proposes a lot of changes and maybe in some points actually implement those changes in the schematic. So it is separated, the schematic design and the layout design, but since this interaction needs to be very close, there are some room to work for the both sides.
So thank you. Another question by Professor Rafael Garibotti from Catholic University at Porto Alegre. First one is, what technology nodes are the projects in Brazil?
I can take this question. So yeah, so all the projects that we are doing now, they are below 7 nanometer. So we worked with 28, as Lazari commented in his slides, but currently we have been working below 7 nanometer.
Thanks. Another question by Rafael. Lumentum has several groups around the world. How do you see Lumentum's grow in Brazil? In which groups of engineers will Lumentum invest more? For example, verification, design.
Yeah, so this is a great question. So we have been our current operation here in Brazil that I mentioned in the beginning of this talk covers not only the DSP, the ASIC team, right? But we also have X-ray systems and also the photonic teams. So in all these technologies, we have about 150 people. Specifically for the DSP, we are looking for people with different backgrounds covering all the ASIC flow, right? So of course, the verification team is I would say that is the biggest one because of the specificities of the products that we are developing, as Lazari mentioned, especially for SoCs that have different modes of operation and so on. So typically, the verification team is bigger. But I have to say that what I can share at this point is that we have opportunities for all the different parts of the flow. So if you see matching on what we presented today, please contact us. That will be very helpful, and we will be very happy to talk to all of you.
Thank you. So if someone have any additional question, please do it ASAP. I have one. In all these designs, you are using several IPs, or how you are working with?
You can comment on that, Lazari.
Yeah, I mean, in the past we use more IPs, and as the time goes, we are reducing because we are creating our own. So in these three main areas, like the core biz, DSP, FEC, and protocols, the goal is to do all with internal developed code. But for more things like available off the shelf, like memories, like PLLs, and PLLs for the digital part, PLLs for the analog is very, very critical. So we develop, but PLLs for the digital, and also like USB if we need, or some low speed interfaces. So in that PVT sensors. So what's common for the industry, like kind of off the shelf and like low end, usually that's this one we acquire, and we try to develop in these three main areas of DSP, FECs, and protocols. So it's like a mix, but in these three core main areas we have been increasing to be all our internal designs, let's say.
Okay, so another question. So you are working mainly in FinFET or also in bulk and FDSOI?
Yeah, for the current products that we develop, only FinFET. So that's the one that gives us, let's say, the best performance and power consumption trade-offs for the current technology.
Okay. So I'm seeing no more questions here in the chat. So thank you very much. I don't know if you have some final comments to say.
No, just thank you, Professor, and all the community for the opportunity to share what we are doing at Lumentum with all of you.
Yeah, thank you very much, Professor.
Thanks.
Thank you to you to give us this nice talk and to provide us the information about Lumentum. So I wish a good progress in growing Lumentum in Brazil. I think you are a very nice group, and I hope to see new achievements in the near future. And also, we hope to see you in person in next event as soon as possible. And
sure.
I also would like to wish all the attendees Merry Christmas and Happy New Year, as well to Daniel, Nelson, and Jacklyn. And so this is the last activity of the CAS chapter, Solid State Secrets, and the EDS chapter in Rio Grande do Sul, as well the Brazil Calcium EDA chapter. So we are going to start some talks in the second half of January. And so have a Merry Christmas, all you again, and Happy New Year. Thank you very much. Bye-bye.
Thank you, everybody.
Happy holidays.
All right.